Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will show that if a random variable has a geometric distribution, its expected value is 1 over p. Okay? Well, before we provide a proof of this result, we are going to need 3 additional results. Okay, let me show you those. Okay, so the first result has to do with series. Okay, so what we have is that the sum of q to the y power, where y goes from 1 up to infinity, is going to be q divided by 1 minus q. We are going to show that result here in this video. Let me show you the other 2 results that we're going to need in order to show that the expected value of a geometric random variable is given by 1 over p. The second result is something that I'm sure you know from calc, that the derivative of a sum equals the sum of derivatives. That second result we're not going to be showing here. Okay? The last one is the derivative of a particular function of q. The derivative with respect to q of this function q divided by 1 minus q happens to be 1 over 1 minus q squared. Again, that's just finding a derivative, and we're not going to be doing it here together. It should be easy for you to do on your own. But let's discuss in more detail the first one. So let's show that one. Proof of that result. Okay, let's show that result. Proof. So this is a series, so it's a sum with infinitely many terms, right? So let me use this notation for the finite version of that sum. We have n terms of that sum. The first one would be q plus q square plus q cube plus so on, plus q to the n power. Let me call that equation, that expression, 1. Okay? Next step, what we're going to be doing is we're going to be multiplying the first equation, equation 1, by q. So let me copy and paste this guy. Let's find q times s n. So if we multiply q by q, we have q squared. This one would be q cube, q to the 4, q to the n plus 1 power. You agree? Let me call that second equation equation 2. Now notice that if we compute the difference between Sn and Q times Sn, so Sn minus Q times Sn, we would have Q plus Q squared, but then this would be a negative Q squared, so these guys would cancel out. We have Q cube minus Q cube, these would cancel out, and so on. So then we would have Q to the n power. The previous term here would be Q to the n power, so the only ones that survive are the first one from the first equation and the last one from the second equation. So let me just say that let me just say notice that Sn minus Q times Sn equals Q, right? The first term of the first equation minus the last term of the second equation. You agree? Now let's try and let's just factor out Sn. So this on the left hand side is equivalent to just having Sn times 1 minus Q. That equals Q minus Q to the n plus 1 power. Okay? Now if we divide both sides by 1 minus Q, what we have is Q minus Q to the n plus 1 power divided by 1 minus Q. Okay? Okay. Now, something that I forgot to say here is that this is provided, right? Provided that the absolute value of Q is less than 1, right? Provided that the absolute value of Q is less than 1. Okay. Okay, now let's talk a little bit about notation, right? So Sn is just as we said at the beginning, a finite version of the series. It's a finite sum. So we have this. Sorry, that should be exponent. So the sum of Q to the y starting at 1 and ending at n, right? That is just Sn. So when we have instead of an n here, when we have an infinity sign, an infinity symbol, what we mean is this. That's just shorthand for the following. This would be the limit when n goes to infinity, right? N goes to infinity of Sn. N goes to infinity. Okay, so it's the limit of that finite sum when n goes to infinity. This is just shorthand notation for this. So now what we want to do is finding the limit, right, of Sn, because that would be what we want. So let me copy this here. The limit of Sn as n goes to infinity of this what would be? Well, note that q and 1 minus q are not affected by n, right? So the only one that is going to be affected by n is this term here, q to the n plus 1 power. But q lives here. The absolute value of q is less than 1, right? So if we have a number that is less than 1 in absolute value, and you have q to the n plus 1 power, and n is going to infinity, the limit of q to the n plus 1 power will be 0. So what you end up with here will be just q, right, because this is going to be 0, divided by 1 minus q. And that's what we wanted to show, right? Okay, so bottom line, result 1 is just that series converges to q divided by 1 minus q. Okay, as we mentioned before, the other two results should be easy to show using, standard knowledge from calc. Okay, let's go back to the main proof. Let's show that the expected value of a geometric random variable is 1 divided by p. As you can imagine, the first step will be just writing the definition of expected value. So the expected value of random variable y in this case would be the sum of y times p of y, the probability that random variable y equals a particular value lowercase y, and we do that the sum of all those products for all possible values of y, and in this case y goes from 1 up to infinity. Okay, so now remember that we have an expression for the probability distribution, for the probability mass function of a geometric random variable, and it looks like this. If you want the probability of needing lowercase y trials to observe your first success, that means that the first y minus 1 trials were failures and the last one was a success. Okay, so let me just rewrite that, the definition of expected value, but now we're going to be using the particular expression for a geometric distribution. So we know it's going to be 1 minus p to the power y minus 1 times p, right? Okay, now let me do a change of, let me label 1 minus p as a q, okay? It's going to be easier to deal with these expressions if I just define q equals 1 minus p. So note that we can also pull that out. That p, we can just place it here outside that infinite sum. So let me do that. And let me change notation again. What I'm saying is just that I will let q be 1 minus p. Okay? Let q be 1 minus p. Okay. Now, here is where our results will prove very useful. Results 1, 2, and 3. First, note that this here, y times q to the y minus 1 power is the same as this. You agree that this is the same as the derivative with respect to q of the function q to the y. You guys agree? If you take the derivative with respect to q of q to the y, you end up with y times q to the y minus 1, right? So we're just observing that q to the y minus 1 is this, and we need that y here. Okay? Right? These two expressions, q to the y minus 1, I'm sorry, we don't need this one here. These two expressions, y times q to the y minus 1, right? And the derivative with respect to q of q to the y power are the same, right? Because when you take the derivative, q to the y, you have y q to the y minus 1 power. Agreed? Okay. Now, note that this is just the sum of a bunch of derivatives. Sum of derivatives. Well, that is going to be the same as the derivative of the sum, right? By result 2. By result 2, sum of derivatives equals the derivative of the sum. Okay, so let's write that down. Derivative of a sum is the same as the sum of derivatives. Okay. Now, note that what we have here is a series q to the y power. right? We have that infinite sum of those terms, q to the y. But that is our first result. Remember that additional result, result 1, the one that we actually showed? There's one here. So we know that that series converges to q divided by 1 minus q if q is in absolute value less than 1, but q happens to be 1 minus p, and we know that probabilities live between 0 and 1, so q in this particular case lives between 0 and 1, so its absolute value is less than 1, so the conditions of that result hold, so we get to plug in what we know from the first result, that that series converges to q divided by 1 minus q. Okay, so let me write that down here. q1 minus q. Okay, and then by result 3, I mean, it's just taking the derivative of this expression. What we said is that the derivative of this expression is given by just 1 divided by 1 minus q squared, if I remember correctly. Yeah, there it is. Okay, so let's use that, and then what we have is 1 divided by 1 minus q squared, right? But now recall that q equals 1 minus p, right? So 1 minus 1 minus p is just going to be p. You guys agree? So what we have here is just, instead of q, we have 1 minus p. When you do that, 1 minus 1, that cancels out, and then we have only positive p. So we have p squared here in the denominator, and then we have p divided by p squared. P divided by p squared, that's just 1 over p, right? And we are done. That's what we wanted to show, that the expected value for a generic geometric distribution is 1 divided by p. Okay, so now if you're able to justify that a random variable has a geometric distribution and you want to find its expected value, you can quickly find it with this formula, 1 divided by p, where p represents the probability of success in any given trial. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.